last number of generations of wireless standards have seen a dramatic increase in spectral efficiency. This increase in bits per hertz has been achieved by new and complex modulation schemes and also the use of wider bandwidths in the radio. However, this increase in spectral efficiency has come at some significant cost in terms of power efficiency of the radio. We now see well over 50% of all the power in the radio being consumed by the RF power amplifiers. And this is really down to the nature of the 4G and 5G signals being transmitted, particularly the high peak to average power ratio of those signals. This high peak to average power ratio, whilst delivering higher spectral efficiency, means that the power amplifiers need to be operated backed off from full scale to accommodate the peaks. And this has resulted in poor average efficiency for those power amplifiers, particularly fixed supply power amplifiers. A consequence of the poor efficiency is the need for larger heat sinks to extract this heat, and of course, higher overall power consumption in the radio. To try and address some of these challenges, one of the things we can do is look at how we can digitally assist the PA and overcome some of these challenges. First of all, by looking at the high peak to average ratio, and by using a technique called crest factor reduction, we can reduce the peak to average ratio of the signaling, thus requiring less back off of the power amplifier in order to accommodate the peaks. And this needs to be done, of course, without impacting the signal quality or the so-called EVM of the signal being transmitted. Another approach here is to try to operate the amplifier in its higher efficiency nonlinear region of operation. And if we can do that, we can further improve the efficiency of the power amplifier and reduce the heat dissipated in the radio. Now, operating in the nonlinear region of the PA can generate undesirable consequences. So a technique to try and overcome this is something called digital pre-distortion. In the demonstration today, we will look at Xilinx's adaptable CFR and DPD IP. This IP can be tuned to cover a wide range of use cases and amplifier technologies. And in the demo, you will see two challenging use cases being addressed with the IP. So this is the bench setup for our demo today. We can see the evaluation board, the CCU102, and the RF transceiver board from Texas Instruments, along with the power amplifier from Skyworks. So this is the CCU102 board. The Zinc UltraScale Plus MPSoC will host the RF IP for CFR and DPD, and also the connectivity IP to the transceiver. So this is the transceiver from Texas Instruments. This is an AFE7769 device. It supports up to 600 megahertz TX and feedback bandwidth to support the expansion, and JESD204 for connectivity to the FPGA. And this is the Skyworks PA. We are using a SKY66318-21. So this is a 200 megahertz PA capable of delivering up to 28 dBm average output power, 3.3 to 3.7 gigahertz. So for the rest of the demo, we will focus in on the DPD demo GUI and the signal analyzer to measure the performance. So this is the DPD GUI. We can set up the test signal here. I've got 5 LTE-20 carriers here, total 100 megahertz instantaneous and occupied bandwidth. And we can activate the DPD. And when we activate the DPD, you can see the feedback trace from the PA on the right-hand side here. And again, you can see the linearized performance from the feedback path once we've activated the DPD. But we can measure the performance on our signal analyzer. So what we're looking at here are those 5 LTE-20 carriers at the output of the PA. This is pre-correction. And once we activate the DPD, you can see the yellow trace, and you can see excellent performance there in terms of adjacent channel power. So we repeat the test, but instead of LTE carriers, we're using one 100 NR 5G carrier here. So again, 100 megahertz instantaneous and occupied. We activate the DPD, and you can see the linearized performance in the trace on the right-hand side there, the feedback from the power amplifier. And again, we can look at our signal analyzer and measure the corrected performance at the output of the power amplifier. So once we activate the DPD, you can see the yellow trace here, which is the corrected performance. And again, we're measuring excellent adjacent channel power, over 50 dBc ACLR performance there with the DPD. So one more harder use case here, where we are generating up to 200 megahertz of instantaneous and occupied bandwidth with 10 LTE-20 carriers. So when we activate the DPD running at a higher sample rate here, 737 megasamples, we can see the correct performance. And now we look at the signal analyzer. And once we activate the DPD, you can see the corrected performance in the yellow trace. And again, 50 dBc, excellent performance in terms of adjacent channel power correction. And finally, we will use our NR carriers, in this case 2 NR100 carriers, to look at the performance of the PA with the 5G signaling. Again, we activate the DPD here, and if you look at the trace on the right-hand side, it's the output of the PA, the feedback path, and you can see the linearized performance of the power amplifier. But let's take a look at the signal analyzer. So there are 2 5G carriers there, 100 NR carriers. Now we will activate the DPD, and the yellow trace will show the corrected performance. And again, as highlighted, excellent adjacent channel power performance. So in the demonstration, we've seen how we can improve the PA efficiency and performance for 100 and 200 megahertz use cases using the 5G NR carriers. To find out more information about any of the components or aspects covered in the demo, please visit the links shown on the screen here.